Hi guys, let's continue our discussion of hybridization by picking up with bond lengths and bond strengths here in the outline. Now you can see your Klein textbook for this information, but I provide you with a table from another textbook. It's on the back of the functional group DUS warm-up. We were looking at it in the previous video. By the way, we'll also at some point during this video look at some structures of common drugs, which is in this syllabus handout. Okay, we ended the previous video by looking at the relative differences in the shapes of the hybrid orbitals. And remember, %S character is a good way to sort of understand what's going on here. The more S character, an SP has 50% S character, it's going to resemble more of the S orbital, and an S orbital being rounder and shorter and fatter, etc. The hybrid is going to be shorter and more rounder. On the other hand, at the other end of the spectrum, the sp3 hybrid, which is only 25% S and thus 75% P character, is going to have less resemblance to an S orbital, and actually thus more resemblance to a p orbital, and thus it is actually longer, more like a p orbital. Alright, we also said that the more S character, these orbitals, these hybrids are going to make stronger bonds, and that's very important to understanding the information down here. So this would make a shorter bond, and this sp hybrid would also make a stronger bond. Now the table down here from the Smith textbook, I'm sorry, this is Bruce textbook, another textbook we used to use here. Begins with a regular alkane, a saturated alkane. Of course, it's redundant. Most alkanes are saturated. Saturated hydrocarbon, I should say. Let's get the terminology correct. Now both of these carbons are sp3 hybridized. Bond angles around everywhere around this molecule are 109.5. Every bond angle is going to be either an HCH bond angle or a CCH bond angle. And they're all 109.5, basically because each carbon is tetrahedral, and that leads to the bond angles around each of those carbons. Now of course this is not drawn correctly. That's not drawn in a 3D tetrahedral nature around either carbon. But again, that's common. We don't always draw the 3D nature of a tetrahedral carbon. But you should be able to if asked to do so. Okay, the length of the carbon-carbon bond, 1.54 angstroms. Alright, you should be familiar with an angstrom. Typical unit of measurement there for bonds. Now, relative, let's look at the carbon-carbon bond length between the two carbons that are double bonded in ethylene. Now really this is referring to the interatomic distance between the two carbons. Alright, kind of broaden that out. The distance between these two carbons is shorter. And in the distance between these two carbons, the bonding distance between them is even shorter. Why is that? Well, it has to do with what type of bonds are making the sigma bond. Okay? The sigma bond here is being made by sp3 overlapping with an sp3. Those two hybrids interacting to make the sigma bond between the two carbons. Down here, this is sp2, sp2. Because each of these carbons are sp2 hybridized, and the sigma bond that is in here is made by overlap of these two orbitals, and this is mainly review. We showed this in the previous video. Alright, you need to go back and review. Right there was our sp2, sp2 overlapping. And then the sigma bond in the alkyne is, of course, sp-sp overlap. And let's look at these orbitals being used, these hybrids. The sp are shorter. And so shorter orbitals are going to make shorter bonds. They have to. Okay? If my fingers were joined together here, the rest of my hand over here where the knuckles are, this part, can be further apart. But if my fingers are shorter, guess what? If my orbitals are shorter, the nuclei over here are going to have to come closer together to make the bond. Alright? If I use longer fingers, well, longer, shorter. You see? I got to come closer together to make the bond. So, as we use longer orbitals, we get longer interatomic distance. Or we can just say longer bond. The sigma bond is what rules here. The pi bond doesn't influence the length. Okay, what about strength of these bonds? Well, what do we say? The more s character in your orbitals, the stronger the bonds they're going to make. So which of these three would you expect to be the stronger bond? Well, this one down here, the sp-sp. Bond strength is quoted either in kcal per mole or kilojoule per mole. I would probably just go with kcal. We don't really need to learn the absolute number. Right now we're just looking at relative differences, the trend here. And we see that this is stronger, but hold on, we have to be careful. This is talking about the entire bonding between the two carbons. A little bit misleading. Now obviously, a double bond is stronger than a single, and a triple bond is stronger than a double. But that's not what is exactly going on here. Because if you look at this, single, double, well, if this was double, that would be 180. This is not 180. Because this is an sp3, sp3. This is an sp, sp2 plus a pi. This is an sp, sp sigma bond plus 2 pi. 2 pi bonds. Single, double, triple. All right. This is the stronger bond, stronger than that. So, but it's not that much stronger. Maybe I'll just throw a number out there. Maybe this is stronger, and it is maybe, okay, a random number here. Maybe it's 100 kcal per mole. All right, which is stronger than 90 for that, as we expect. But then you also get the pi bond, the strength of the pi bond, and in this scenario, that would leave 74 more. For the pi bond. Now if we get down here, this bond here, the sigma bond, maybe that went from 90, maybe to 100, maybe this is 110. But then you have 2 pi's. And if the 2 pi's are each 74, let's call them identical. 74 times 74 would be what? 148. 148. That would give us 258. And that's how we get up to this type of number. Now I sort of just estimated the 90, 100, 110. What I'm telling you is that this is the number for all the bonds. And unfortunately, they didn't provide a number for just the sigma bond of this and this. All right. Let's look at length of CH bonds. Well, what type of orbital is being used here? This is going to be an sp3 bonded to an S, because the H uses just the s orbital. This would be sp2 to S, and this would be sp to S. Which bond do you expect to be longer? Well, the one that's using the longer hybrid orbital. So this would be longer. And then shorter would be the one that's using the shorter hybrid. So it would be shorter. And indeed it is. You see 1.06 angstroms. It's the shorter bond. Now note that these are not that big of a difference. But we do understand and we can predict the trend. As we come down, we expect the bond, the CH bond, to get shorter. Same thing with the strength of the CH bond. Now this is more clear than this over here ended up being. We just have one bond. Which of these three bonds is going to be stronger? Well, the one that uses an orbital with more S character, that would be this one. The sp is going to make a stronger bond. Again, everyone is using the S on the other side, so that's consistent. We have a stronger bond here. The CH bond is stronger in ethyne. So, again, percent S character helps us understand bond strengths, relative bond strengths, okay? Relative, compared to each other. Bond strengths and also bond lengths. All right. Now again, as we said in the previous video, the main reason that this orbital makes a stronger bond is because it's a more stable orbital. The electron is more stable when it's in this type of orbital. That's just because it has more S character. And you know that an S atomic orbital is more stable than the corresponding p orbital in the same shell. Okay, next on the outline. Other hybridization examples. Carbocations. All right. Let's look at molecule CH3. Well, that's a carbon with 3 H's. I'm just going to quickly draw them around and then not worrying about geometry yet. Wait a minute. Carbon doesn't have an octet. And how many valence electrons do we have? Carbon has 4, each H is 3, 7. Well, hold on here. Hold on here. We're doing more than CH3. We're doing CH3 ion. Okay? I told you it was an ion, positive. That means it's missing an electron, equals 6 electrons. Okay? It's missing one of its valence electrons. Ultimately, it's a carbon with 3 H's, and that's it. 2, 4, 6. There's no more electrons here. There's no lone pair. Look, the carbon doesn't have an octet. We can't make another bond because we don't have any more electrons. We've already used all 6. This carbon is not typical, not standard. If it's not standard, it's likely going to have a charge. This carbon is positive. Why is it positive? Because it owns 1 for each bond. It owns 1, 2, 3. It owns 3 electrons. It's supposed to own 4 based on the periodic table. It's in group 4. It's missing 1. And if you're missing an electron, your charge is plus. There we go. There is a positively charged carbon called a carbocation. All right. A carbon cation, we shorten that to carbocations. And we will see carbocations very often throughout the course. It is possible. But the question here is, what's the hybridization of that carbon? And what's the exact geometry of those bonds around that carbon? And the first question we want to ask is, how many electron regions? And that would be 3. Single bond, single bond, single bond, 3 regions. And these are the same questions we asked on the previous video. And 3 regions is going to be what type of hybridization? It's going to be sp2. Okay? Because, or I can ask this, what geometry do we expect for 3 electron regions? Trigonal planar. If you tie 3 balloons together, they will spread out in a trigonal planar arrangement. If you put 3 electron regions around a carbon, they will spread out in a trigonal planar arrangement. But sp2 essentially means trigonal planar. All right. Now that we've got that far, what is the graphing of that going to look like? Well, trigonal planar is, or sp2 is three sp2 hybrids, yeah, and a p orbital left over. Now again, if you don't remember that for sp2, you need to go back on the previous video and exactly right here. Okay? 3 hybrids and then the p orbital. All right? That is an sp2 setup. Now the question becomes, what type of bonds do you see? I see 3 sigma bonds to hydrogen. Single bonds are always going to be sigma bonds. And what type of orbitals do we use to make sigma bonds? We use hybrids. And so what we have going on here is a sigma bond to H, a sigma bond to H, and a sigma bond to H. The 3 arrows represent the 3 valence electrons of the carbon. Each H represents the hydrogen nucleus, but also it really represents the H electron. And so the magic here is an H electron and a carbon electron bonding together to make a magical two electron covalent bond. And we do that 3 times, and that's shown here. This is how we graph hybridization, and how I want you to do it. Note, the p orbital is empty. Empty p orbital. Now, we could have up here said, does this compound have an octet? No, it only has 2, 4, 6 electrons around it. 2, 4, 6. We get to share the H's in the count. It does not have 8. We kind of see that here. One of the orbitals is empty. It's actually a p orbital. All right. Now, before we move on to the next example, let me ask you this. Do you think this compound, this ion, would like to have some more electrons? Do you think this compound likes or wants electrons? Yes. It would love to fill this empty p orbital and thus fill the outer shell. And something that likes or wants electrons is going to be called, Well, let me ask you, if something likes wine, we might refer to that person as a winophile. Molecule that likes electrons is called an electrophile. Or as an adjective, we would say it is electrophilic. All right. Another important term here is, why do we say yes? Why does it like or want electrons? Because it's electron poor. So why does it like or want electrons? Because it's electron poor. You see, it's missing an electron. It's electron poor. It's thus considered electrophilic. It's an electrophile. Now keep in mind, this is not the same as electronegative. That's a very different term. This is probably a new term for you. I'm introducing it now. We'll use it more and more, particularly when we get to test 2 material. Okay, that is a carbocation, and we graph the hybridization. Next, let's look at a carbanion. We can have CH3 minus. Now, again, we want to put the charge as closely as we can to the charged atom and circle it. On the handout, it's hard for me when I'm typing to circle something, so it's not circled. But when you're writing, circle your charges. Okay. Now let's look at this. By the way, we didn't talk about geometry back up here. We actually stated it. It's trigonal planar. Carbon. These H's are around this carbon in a trigonal planar arrangement, like this. And each bond angle is what? Each bond angle is 120 degrees. Yeah, trigonal planar. That p orbital, that empty p orbital, is perpendicular to that. It's half up and half down. Or if you drew this on the board, it would be half coming out at you and half going behind the board. What about the CH3 anion? Carbon with 3 H's. But that's just here. It's an anion. The only way it's going to be an anion is for it to have a lone pair. And now, charge of this carbon, 2, 3, 4, 5. It owns 5. It's only supposed to own 4. It's got an extra electron, and thus the charge is minus. Now we will occasionally see carbons as minus, not as often as they are positive. Carbon is very often positive, only much less common negative, but when it's negative it's called a carbanion. That's short for carbon anion. Okay, what hybridization do we expect for this carbanion? Same questions as above. How many electron regions? Four. Single bond, single bond, single bond makes 3. Lone pair makes 4 electron regions. 4 electron regions are best spread out in what geometry? Tetrahedral. What type of hybridization will this be? Well, if you need 4 regions, that means you need 4 hybrids, and to get 4 hybrids, you're going to be sp3. And tetrahedral and sp3 basically mean the same thing. So that's what we're dealing with here. If we show sp3 hybridization set up, we would have 4 sp3 hybrids. That's it. There's no p orbital left over. We mixed all 4 original atomic orbitals. Look back at the previous video. Hopefully you're with me. Now, what type of bonds do you see here? I see a sigma bond to H, a sigma bond to H, a third sigma bond to H. And what else do we see on this carbon? A lone pair. A lone pair sits in one orbital by itself. It's a non-bonding pair of electrons. We call it a lone pair. I abbreviate it as LP. There you go. One of the hybrids has a lone pair. It's not bonding to any other nucleus. Can we draw this? Carbon, tetrahedral. 2 in the plane, 1 forward, and 1 back. And I'm not going to do orbitals here, but I'm just going to do the magical dash there. This is an sp3 overlapping with the s of the H there. Where do I want to put the third bond? I'll do it forward. Okay. Well, what's occupying this region? Well, it's an orbital, but that orbital is not interacting with any other orbital. Instead, that's just a lone pair projected into that region. Now, it's the entire region if we want to draw that real quickly. Orbital, 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 H, H, H. All right, that entire orbital there contains that lone pair. Over here, I just sort of drew it on the end because there really wasn't anywhere to show it. I didn't want to write it on top of my projection. All right, it's tetrahedral. The lone pair is in what type of orbital? Well, it's in an sp3, one of the hybrids. All right, let's keep at it. As we do more examples, we'll see what type of questions we can ask and answer. Atoms other than carbon. All right. Let's look at the structures of some common drugs page in the syllabus handout. And let me ask you, okay, what is the hybridization of this N-nitrogen in Cipro right here? Well, the first thing we need to know is how many lone pairs are on that nitrogen. We need to have a complete Lewis structure, and that nitrogen has 1 lone pair. Standard bonding, 3 bonds, 1 lone pair. All right. Back over here. Well, the first question we ask is how many electron regions are around the atom. It doesn't matter if it's nitrogen, we're still going to ask the same questions. All right. 4 electron regions. Bond to carbon, that's 2 regions. Bond to H, that's a 3rd region. And lone pair is going to be the 4th region. What type of hybridization do we expect? Well, we're going to expect sp3 slash tetrahedral. Until we have an exception. And we will see an exception in maybe the next example. There's no exception yet, though. Now, we don't often show the full geometry of a tetrahedral atom. If we did that, this nitrogen here okay, that's to the benzene ring up there. I'll just cut that off. Nitrogen, 2 in the plane, 1 forward, that'd be the H, and then something in the other orbital is going back. What is that? Well, that's actually the lone pair, again in that full orbital. There's a tetrahedral nitrogen. This is not shown that way, and actually the bond to the H is not shown out. It's shown partially condensed. You need to know what type of geometry we're really looking at there. Now let's graph that geometry. Well, since it's sp3, it's a lot like what we just did. 4 hybrids. What type of bonds do you see for sp3 hybrids? What type of bonds do you see this nitrogen making? Sigma bond to carbon, sigma bond to carbon, here and here, sigma bond to H, and then one of the other hybrids has a lone pair. And that is actually isoelectronic to the previous example. This was a carbon with 3 bonds and a lone pair. This is a nitrogen with 3 bonds and a lone pair. Same hybridization. The only difference here is the carbon in this situation is an anion, but nitrogen, which is supposed to have 1 more electron, is actually neutral in this situation. Otherwise, they are isoelectronic to each other. This and the, okay, that is, this looks the same. So we graphed the hybridization of that nitrogen. Let's try the other nitrogen here. First off, we know there's a lone pair there. All right. How many regions around that nitrogen? And the answer here is, well, there's 4 electron regions, but we have something unique going on here. But here the LP is conjugated. What does conjugation mean? Conjugation is p orbitals lined up. That lone pair is conjugated with the neighboring p orbital. All right. Look next door to this nitrogen. Do any of the atoms bonded to that nitrogen have a p orbital? That one does not, that one does not. But over here, this carbon is sp2 with a p orbital, because an sp2 hybridized atom has a p orbital. And here's a statement. Anytime a lone pair is next to a p orbital, the lone pair is going to want to be in a p orbital. All right. Thus, the LP is in a p orbital. And the only way for that lone pair to be in a p orbital is for the nitrogen to have a p orbital. And it's going to have to be sp2. Because an sp3 hybridized atom does not have a p orbital. That nitrogen is sp2. We will do more examples like that. But since I told you that, now let's graph it. An sp2 hybridized atom has 3 hybrids and then a p orbital. What type of bonds do you see this nitrogen making? 3 sigma bonds to carbon. Bam, bam, bam. Sigma bond to carbon, sigma bond to carbon, and sigma bond to carbon. Where's the lone pair? Well, we said it right here. The lone pair is in a p orbital. Right here. We're going to put it right here. Boom, boom. Now the valence of nitrogen is filled by making 3 bonds and then having a lone pair. So these 2 nitrogens are very different. In one case, the lone pair is in a p orbital. In the other case, the lone pair was in a hybrid, in particular an sp3 hybrid. This lone pair is going to be basic and reactive. A relative term. But basic, though, it's going to act as a base. Lone pairs that are in p orbitals are typically not basic / not reactive. Now that's a simplified statement. We will see exceptions to this. So in some cases the lone pair may be slightly basic for some other reasons. I'm giving you a take-home message here. All right. You should certainly know, if looking at this ring, and if you were asked which of these 2 nitrogens is basic, you would know it's the one on the left if you understand hybridization. Now, the other nitrogen is going to be the same as this one because there's a lone pair there, but next door is a p orbital. Now actually, if we graph that real quickly, like we did here a little bit, you've got the benzene ring, and every atom in the ring has a p orbital. If you look at it, that's our definition of aromaticity. Coming off is that nitrogen, 2 bonds to carbon. The ring has electron, 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 electron. Pi bond, pi bond, pi bond, but there's also bonding here and here. That's aromaticity. Important thing for us now is this lone pair wants to be in a p orbital too. Because if we put it in the p orbital, now I drew that sort of large compared to here, it can interact with the neighboring, it can play along with the p orbitals. And that's called conjugation. Conjugation of p orbitals. Same thing's going on over here. This lone pair is conjugated with that p orbital. That lone pair is in a p orbital. Okay, let's do some other examples. Want to switch to oxygen? We asked the same questions. What about the oxygen of Tylenol, the upper, the carbonyl of the amide? Graph the hybridization of that oxygen. I'll give you a little time to do that. Okay. How many electron regions around the oxygen? Double bond is one region, lone pair, lone pair. 3 electron regions. That is going to equal sp2, which is trigonal planar. Let's graph that. Well, sp2 is going to be hybrid, 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 3 hybrids, and then 1 p orbital. And a question that I will eventually ask you is, what type of orbital is this lone pair in, or both of the lone pairs? What type of orbitals are they in? Well, here's our sp2 setup, which we got from asking this question. Now, what type of bonds do we see? This oxygen making. All right. This oxygen, okay, this is where the oxygen. It is making a sigma bond to carbon. See this double bond? It consists of a sigma bond to carbon, and then a pi bond to carbon. And the pi bond is made using the p orbitals. And there's your double bond, your 2 bonds, a sigma and a pi. All right. We did this in the previous video when we looked at ethylene. Double bond. It doesn't matter if it's an oxygen-carbon double bond or carbon-carbon double bond. We ask the same questions. Now, where do the lone pairs go? You got 2 lone pairs. Well, they can only go one place. One goes here, and the other goes here. So, and we're done. This is your double bond, and these are your 2 lone pairs in sp2 hybrids. All right. Now, you want to show that we have oxygen. This is trigonal planar. We can go ahead and sort of do trigonal planar. Hopefully that looks trigonal planar. This is bonded to carbon. Coming down as a bond. That's that. The other 2, part of the trigonal planar, is lone pair and lone pair. Then what else is on this oxygen? p orbital. Now the p orbital is actually straight up. All right. I'm going to have to kind of draw it something like this. But the carbon also has a p orbital. All right. It's also sp2. And I could have drawn them more straight side to side instead of one turned a little bit. In any event, there's 1 electron here, and there's 1 electron here, and these are interacting side to side. And so between the oxygen and carbon, you have a sigma bond and a pi bond. Sigma bond and a pi bond. The trigonal planar arrangement is shown in that sigma framework in there, the original 3 dashes. Now, if you wanted to graph this carbon, well, it's also sp2. Boom, 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 boom. That carbon is making sigma bond to carbon, sigma bond to nitrogen, sigma bond to oxygen, and pi bond to oxygen. There's your double bond to oxygen. That's graphing that carbon there, where up here we focused on the oxygen. Is that right? Sigma bond to carbon, sigma bond to nitrogen, and then a double bond to oxygen, sigma and pi. I think that's right. Okay. Ultimately, every one of these atoms you can graph for practice until you get comfortable. Want to try one more? How about the oxygen, the ether oxygen of naproxen? I'll give you some time to do that one. Keep in mind, if a lone pair is conjugated with a neighboring p orbital, if that's the case, then the lone pair, you want to make sure it's in a p orbital. Okay, this oxygen has, of course you can pause the video and work on the problem. I'll continue ahead. The oxygen has 2 lone pairs. Alright. There are 4 electron regions around that oxygen, but we have a case where we have a lone pair next to a p orbital, because this carbon has a p orbital. One of these lone pairs is going to want to be in a p orbital. Alright. One of them there, but only one, so these can interact. That's called conjugation. So we need one p orbital here, and that's going to be sp2. sp2 is, of course, again 3 hybrids and a p. And now we ask, if we can still see it, what type of bonds is this oxygen making? Sigma bond to carbon. Okay. What is an Me? Me equals methyl. And of course a methyl group is a CH3 group. That oxygen is bonded to a CH3. That oxygen has sigma bonds to 2 carbons, 2 different carbons. Sigma bond to carbon, sigma bond to carbon. Then it has 2 lone pairs. Well, guess what? One lone pair is in a p orbital. We said why? Because if we put a lone pair in a p orbital, then that p orbital and that lone pair can interact with the neighboring p orbital. Where's the other lone pair? Well, the only place it can be is in the hybrid. And so we end up with 1 LP in a p orbital and 1 LP in a sp2 hybrid. And if we tried to draw that, we have 3 hybrids are going to be spread out trigonal planar. Boom, boom. Does that look trigonal planar? This is coming over to a carbon. One of these is coming down to a carbon, to a CH3. And then what is the other region of the sigma framework? Well, that's just a lone pair. There's your trigonal planar, 120-degree bond angle between COC. There's also a p orbital. It's hard to draw that in. It's actually straight up. But let's try to just draw it in. And there is a lone pair there. Now this is bonded to something else. It's bonded to its trigonal planar. It continues on. There's 6 p orbitals all around this ring, making it aromatic. But this lone pair in the p orbital gets to interact side to side with the neighboring p orbital. And that's a very good thing. That's why, even though it has 4 regions around the oxygen, it instead adopts an sp2 trigonal planar arrangement so it can achieve this conjugation, this p orbital overlap. Lone pairs conjugated, lone pairs interacting with a neighboring p orbital is a stabilizing effect. It's almost like sort of partial bonding. Increased amount of orbital overlap. Good thing. Okay, you can practice any atoms on here. Particularly you want to look at the heteroatoms, but including carbon. Any of these carbons, any of these heteroatoms, especially nitrogen. For example, these 2 nitrogens here, I would certainly recommend, well, maybe starting with those. That's a good place to start. Certainly there, but any of the nitrogens. Lots of nitrogens here. Graphing all these and answering maybe questions like this. Is the nitrogen basic and reactive, or is it not basic and not reactive? Okay, I'll end this here, but I'm sure there will be questions, and probably want to do a few more of these at some point. Let me end by saying that I think I like graphing the hybridization, and I do it much more than most any other instructor, because I really think it helps organize your thinking. You know, and if someone comes out and says, hey, you know, this lone pair here on this nitrogen, what type of orbital is it in? Okay? Well, you can quickly get that answer. You don't have to memorize anything. You have a systematic approach to sort of getting there with some questions you want to ask. And so the graphing, I think, can be very powerful for you to get you the answers you need. That's why I asked you to do it. There's also one page in my workbook where I ask you to do some graphing, and then there's some answers in the answer key section. Okay, guys, so that's one of this follow-up video on hybridization.